Okay, so areas of triangles and quadrilaterals. Okay, so it's a formula-based section. A lot of this just comes down to knowing the formulas for the various areas and being able to use them. I want to see all phones and stuff away, please, or I'm going to start collecting. Stay away, please. So if you know the areas, it's not that big a deal. You're just going to plug in numbers and simplify and get an answer. But the hard part sometimes is knowing how to find the numbers that go into the formulas. Okay? And sometimes that can be a little bit tricky. There are going to be some cases, we'll look at one example today, but you'll see some others on the homework, where, for example, what do you choose to be the base of an object? For example, a triangle. A triangle, I could orient a triangle so any one of the three sides I could call the base, right? But which one is the most convenient to actually call the base, right? It depends. It depends on what's given to you, what information about the triangle is given to you. And so we'll look at some examples like that. Now, before we get into this, though, I want you to notice something here. I want you to notice something. Hopefully this light's going to go on here a little bit. The area of a square. Now, we all know what the area of a square is. Right? If I have a square of side length S, then what's the area of the square? If the side length is S,
S squared.
S squared. S times S or S squared. What did you just say? S squared. So the area of a square is S squared. You suppose that's an accident that we call it squared? I don't think so, right? The most basic unit of area, and think about the units we talked about. If you measure the area of a poster, it's going to be in square inches. Or if you measure the square footage of a house, it's in square feet. The most basic unit of area, or at least if we're thinking about things in a rectangular sense, like on an XY plane, it's just going to be 1 unit of width times 1 unit of height, right? It makes a square. So square is the basic unit of area. The area of a square, therefore, we call, side length squared. I don't know what came first, the chicken or the egg here. I don't know which is, if we called it something squared first and then decided that's what we should call the shape, or did we name the shape first and then decide that that's how we represent the area? I don't know. But obviously they go together, and that's an important observation that I want you to see. When you say, if I say something like x squared, the x squared is coming from the area that I would create if I had a shape with base x and height x. Okay? So the area congruence postulate, very, very straightforward. Falls into the category of, does this make sense? If two objects, two polygons, it could be quadrilaterals, could be triangles, could be anything. If two polygons are congruent, first of all, what's that mean? If two shapes are congruent, they have the same what? Same
lengths.
Okay, yeah, you're getting more specific than I want. Same blank and blank. Could one be bigger than the other one? No, you're getting too specific. I just want totally generally speaking. If two objects are congruent, they have the same size and shape, exactly. Same size and shape. Okay, which essentially means that they are completely overlappable, right? They overlap perfectly. So then doesn't it make sense that if two objects are congruent and therefore have the same shape and same size, that they must also have the same area, right? Okay, it's an easy extension there. So that one's a piece of cake. This one down here seems pretty simple also, but it's very, very useful. We're going to make liberal use of this today. And coming up, we're going to develop the area formulas for all the quadrilaterals just by kind of cutting and pasting and copying and pasting and making simple shapes out of complicated shapes, which we do a lot in geometry. Later on in the year, when we start talking about volumes and surface areas, we're going to create some pretty complicated looking shapes and calculate volumes and surface areas of these things simply by cutting up the composite shape into a sum of simpler shapes. And then we can take those one at a time and kind of add them up. We can do that with areas even more easily. As long as the area of a region is just the sum of the areas of its non-overlapping parts. It doesn't say anything about how we choose to arrange those. I could take a shape and I could cut it and rearrange it, and as long as the pieces don't overlap, has the area changed? If I say I take a piece of paper and I cut it into some pieces and then I move the pieces around, as long as the pieces of paper don't overlap, and I tape them back together, have I changed the area? No, the area is still the same piece of paper, right? Okay. All right, so the first thing then, we just got to remind ourselves, and then from here we'll be able to build the other areas from this one piece of information. What's the area of a rectangle? We know that, right? If this is the base and that's the height, base times height, right? Agreed? Okay, now this is kind of a cool little web page that I've got it on the geometry page, so you can go to this later if you want to. Let me pull this up. AJ, stop talking. Last one. Okay, so what about this? Parallelograms. I want to come up with the area of a parallelogram, and I want the area to be in terms of the measurements that I've got here. Look at the measurements I have for this parallelogram. I have height and I have base. When you think about bases and heights and all this stuff, imagine this in your mind. Here's the mental picture you're creating. I'm taking the shape and I'm going to set it on a glass coffee table, so its base is resting on the coffee table. And the height is always going to be the vertical distance from the coffee table to the highest point on the shape, to what we might call the top of the shape. Okay, so you can all picture that, right? Here's our coffee table down here, and here's our tape measure that's lined, perpendicular to the tabletop, so it's vertically aligned. It measures how high is the top surface of this shape above the coffee table there. That's always a good mental representation of height. So what could I do to this shape to, I'll give you a hint, I'm thinking cut and paste here, to turn it into a different shape that's easier, has an easier area formula. And the only one we know right now is a rectangle. So could I make a rectangle out of this? Yeah, pretty easily, right? If I were just to cut that triangle out and paste it right there, has the length of the base changed? Same, right? Has the height changed? No. Well, what's the area of that rectangle? Base times height, right? Well, if the area of that rectangle is base times height, and I haven't overlapped the pieces, then what must be the area of this parallelogram? Base times height, right? It's easier to see the area when it's a rectangle, but I haven't changed the area by transforming it back to a parallelogram, right? So there's a new formula for us. The area of a parallelogram is just base times height. Okay, and we can see that if we go back to there's our formula. Area of a parallelogram is just base times height. Okay, let's try another one. Another trick. What could I do to this triangle here to create a shape that's easier? And now I've got two of them, right? Now I know two formulas that I could rely on. I know that the area of a rectangle or a parallelogram each have base times height as the formula, right? Could I turn that triangle into one of those two things? In this case, not by cutting and pasting, but maybe by copying and pasting. What do you think? Casey? Yeah, I could copy the whole thing, paste it right there, right? Now, what have I created? What is that? No? Parallelogram. Okay, now how does the base of the parallelogram compare to the base of the triangle? Think coffee table. Here's the coffee table. Has the base changed? No. Base is the same. Has the height changed? Height is the same, isn't it? For the parallelogram and the triangle? What's the area of the parallelogram? Base times height. And so we kind of could have predicted this. We knew the answer to this one before we even started. But then what must the area of just the triangle be by itself if the whole parallelogram is base times height? Half of that, right? Because I doubled the area to make the parallelogram, right? So therefore we now know, and we knew this before probably, the area of a triangle is just 1/2 base times height. Okay, good, good. So we can add another one to our list. Scoot down a little bit here. Okay, sorry, I had to turn all these back. Okay, so now what about a trapezoid? Trapezoid's a little trickier. There's a couple ways we could do this, but I think the easiest way here is not to cut and paste, but rather to copy and paste. Anybody have an idea how I could do that? Ah, okay. So what if I copy this whole thing, turn it upside down, and stick it right there? That's what you meant? Okay. What shape have I created? Parallelogram. Okay. Now, what is we can see that the length of the red base is we calling B1. The length of the blue base we're calling B2. So what's the length of the base of the whole parallelogram here? What do you think? Yeah, one red base plus one blue base. So B1 plus B2 is the base of the whole thing, right? What's the height of the whole thing? Just h. So the area of that parallelogram then, the area of the parallelogram must be 1/2 times the base times the height. So 1/2 times height, or I could put the base first, it doesn't matter, times my new base, which is both of them combined. B1 plus B2, right? I'm sorry, I didn't want the 1/2 there, did I? Because it's just height times base. Whoops, my mistake. Right? Does that make sense? Base times height, or height times base doesn't make any difference which order. So now, what about the trapezoid? If I want to turn this into the trapezoid again, what do I have to do to that area of that whole parallelogram? Yeah. Right, I got to divide it into it's going to have half of that total area. So the area of the area of the trapezoid must be 1/2 times the height times the sum of the bases. So there's our formula, right? And we can get it just by playing this little geometry game, this little mental game where we're just going to cut and paste and copy and paste. So if you ever forget, you can always come up with that again. And there we go back. Okay, what about a rhombus? This one is a little bit trickier. What about the rhombus? Now, if you look at this rhombus here, notice that, well, what's one way we could calculate the area of a rhombus that we already know? Base times height, because what is a rhombus? Yeah, a rhombus is a special parallelogram, right? And so we should, whatever the formula is for calculating the area of a parallelogram, of course, has to work for a rhombus, because a rhombus is a parallelogram. But what if I don't know the base and the height? Like in this case, right? I'm not given the base and the height. In this case, I'm given different stuff. In this case, I'm given the red diagonal, which we're calling D1, and the blue diagonal, which we're calling D2. So our goal here, our challenge is, can we come up with an area formula for a rhombus that depends on the diagonals and not the base and the height? AJ, put that away. Don't get distracted. Put it in your pocket. Put it away. What do you think? What can we do? Janelle?
Aren't the little angles 90 degrees on the inside?
They are.
So you go a squared plus b squared. Wait.
Now you're on to something.
Is it the hypotenuse or something?
Kind of.
This side?
Is there anything I can do with those triangles? Yeah, could I copy and paste the triangles? Now watch this. This is kind of tricky. If I take each of those triangles and I rotate them around 180 degrees, right? Copy them and rotate them 180 degrees. Look what I create. Now what is that? That's a rectangle, isn't it? Right? Everybody agree? Okay, now what is the base of that rectangle? I know it's tilted upward, but imagine that it were to fall back down into place on the coffee table. What's the length of the base? Okay, yeah, what do we call that though? That's just what we call D2?
Yeah.
Everybody see that? D2 would be the base. What's the height? D1, right? So the diagonals in this case represent the same distances as the base and the height. And so what's the area of that rectangle in terms of the diagonals? D1 times D2. Okay, so then what about the original rhombus? 4?
No, half.
Half, right? right? Because didn't I think what I did, I cut the original rhombus up into 4 triangles, and I just doubled each one. So doesn't that mean I'm just doubling the area of the whole thing? I did it in 4 pieces, but I just doubled the area. And so the blue area must be half of the total area, and so there's our formula for a rhombus. The area of a rhombus is just 1/2 the product of the diagonals. And then that trick was so slick, we can even do it again. If we have a kite, we can do the same thing, can't we? If I take each of those triangles and I copy them and rotate, copy them and rotate them 90 degrees. Can I do that? No, I can't. All right. Anyway, I get the same thing, don't I? 1/2 times the product of the diagonals is my answer. Okay, so let's summarize that. If we take a quick look. I don't know. We might. If I got something else, I might do instead. We'll see. Okay, so anyway, take a look, please. We got quick summary here. We know area of a triangle, 1/2 base times height. We said area of a trapezoid was, this looks a little complicated, but wasn't it just 1/2 times the height times the sum of the bases, right? And then we said areas of kites and rhombuses are both 1/2 times the product of the diagonals. It's all right there. It's all in your book. This PowerPoint's online. The formulas are easy. It's just a matter of applying them. But here's what I meant. Take a look at this one. Here's what I meant by choosing your base wisely. If I take this parallelogram and I want to calculate the area, now the way it's currently resting on the coffee table, what's the base? 12. It's got AD, it's got a length of 12, right? Okay, now the way it's currently resting on the coffee table, what's the height?
16.
No. What? It's not 16, because remember...
9.
Oh, okay. Actually, okay, you're looking ahead. If we reoriented it, it might be 9, but the way it's currently sitting, we can't see the height. Notice this 16 is a slanted measurement, right? It's the measurement of the length of that side. It's not the vertical measurement that we need, right? We don't know the height. It's not given to us. Maybe we could calculate it by doing some tricky stuff, but it's a little bit of work. We could make this easier. Could I just reconfigure or reorient that parallelogram so that the base was something different and we had a base and a height? Right? What if we took the whole thing and we set it down so this was the base? See what I'm getting at? Right? If that became the base and that were lying horizontal on the coffee table, then wouldn't this be the height? Because that's a right angle.
Yeah.
Right? The height is the perpendicular distance between the two bases, right? Does that make sense? So then I would just have 16 times 9 is 144. So it all depends on which side you consider to be the base. In this case, definitely there's one way that's preferable. Makes it much easier. Okay, got another question for you. We said that if 2 triangles are congruent, they definitely have the same areas, right? Could I draw different triangles that have the same dimensions, the same base and the same height, and therefore the same area, that are not congruent? I could, couldn't I? What would that look like? Well, okay, try this. What if we've got, let's say, I gotta fix this. Why this thing is?
It's because Brayley's a freshman.
Is that what it is?
Yeah, it's because she's Victorian. Hey, it doesn't matter how old you are. Dude, my dad acts my age. Like, come on now. Dude, my dad is video games and street racing all the way. He doesn't really street race though. He just tried to.
Okay, so
10 on.
Oh, well, this is close enough. Okay. So there's a triangle, right? I'm not going to change the base and the height of this thing, but I want you to see what happens. So here's the base, here's the height, right? I'll leave those segments the same. Let's create a different triangle that's got the same base and the same height that looks dramatically different. How about if we copy that one? So there's the height, right? Let's copy this one, so it's got the same base. Okay. But here's my triangle. This one.
That's pretty cool.
Okay. Those two triangles have the same base and the same height. So do they have the same area?
Yep.
Yeah, they do. Because 1/2 times the base times the height is the area. They look pretty different though, don't they? Right? So that clearly illustrates that just because they have the same area and they have the same base and the same height doesn't mean they're congruent. Okay, now is this a little strange? Do you see that even though this segment right here is outside of the triangle, it's still the height? Because think how we defined the height. The height we said was the vertical distance from the surface of the coffee table up to the highest point on the shape. Right? Now we call this in geometry, we call this kind of a segment, we call this an altitude. We don't do a lot with that this year, but I want you to be aware of that. So what in geometry, the words we use a lot of times, if we want to draw a segment like that, is we say we're going to drop an altitude, meaning we're going to, it's kind of, it almost sounds like what you're doing. If this is the ground, right here, we're going to go up to the highest point on the shape, and it's like dropping a plumb bob down. You know what a plumb bob is? Plumb bob, when you're building and you want to get a straight vertical line, how do you do that? Well, you just take a weighted string and you hang the string from something, and then the string's going to hang in a straight line, and so a lot of times you'll put chalk on that, and you can snap a chalk line on a wall, and you can make a vertical line that way. That's very accurate, very vertical. So the same kind of thing here. If we were to drop an altitude down from the highest point, imagine a plumb bob hanging down off the top of that shape, then the altitude can be, which measures the height, right? The altitude and the height of a shape are the same thing. So even though that altitude is outside of the triangle, it's still how you measure the area. It's still a dimension of the triangle, okay? All right, so one last thing here. I want you to see this guy. Okay, you're going to do some problems like this. Now, I'm going to claim, stop, seriously, I'm tired of this. You got to pay attention. You can't be doing all this stuff. You got to stop. All I'm giving you are the coordinates of the vertices. We've done some stuff like this, right? We've calculated areas, and we've shown that things are parallel by using, we've got two methods. We've calculated distances using the distance formula, and we've calculated slopes. And then we've done a lot of stuff with that. I'm claiming here you don't have to do any of that hard stuff. If I want to calculate the area of this thing, I don't need the distance formula at all. I could use it, but I don't need it. What kind of shape is this? It's a trapezoid, right? So all I really need here, if it's a trapezoid, I just need the lengths of both bases and the height, right? Now if I were to draw those in, here's what they would look like. Okay, how can I get these distances without the distance formula? This is the challenge. Okay, here's the base, right? Or there's one of the bases. So the orange segments are the bases. The pink segment is the height. Agree? How can I get the lengths of the orange segments? Do I need the distance formula? How come? What's the length of that top orange segment? It's not very straight. Pretend it is. 3. How'd you get 3? Okay. Okay, if we were to use the distance formula, it would work. But notice that the y coordinates are the same, right? And whenever if I have 2 points and the y coordinates are the same, doesn't that mean that they're just horizontally aligned? Right? If they're horizontally aligned, all I've got to do is measure how much the x coordinate is changing because the y coordinates are staying the same. All of the motion is horizontal there. There is no vertical motion. Very simple. So x is changing from 2 to 5, and so that's what, 3?
Yep.
Okay. What about the bottom one? 7. I'm going from x equals 1 to x equals 8, so that one is 7. Now what about the height?
You go 7 minus 3. That's not right. Get a ruler.
No? Don't need a ruler. Okay, let me ask you this. This will help. This will help. What are the coordinates of that point right there? Because you can know. You can tell me what they are. What's the y coordinate of that point?
1.
1. How do you know?
Because we're intelligent.
Okay, I agree. But what's your justification?
Because I said so. Coming from Bradley.
What do you think? Yes.
Oh, that's right. Both the other
Okay, yeah, look at these 3 points. All 3 of these points are aligned horizontally, aren't they? So if they're aligned horizontally, doesn't that mean they have to have the same y coordinates? Right? I don't have to get from this point to this point, or even to that point. I don't have to move vertically at all. I just move horizontally, so the y's all stay the same. Now, what's the x coordinate of that point?
8.
No? Is there another point, let me ask you this, is there another point up there that would have to have the same x coordinate as that point?
Oh.
Yeah. That point right there would have to have the same x coordinate because it's lined up vertically with it, right?
Yep.
Agreed? Okay, so this is 5. So now that we know the coordinates, you tell me, what's the height of this thing? 4, because I'm going from y equals 1 to y equals 5, so the height must be 4, right? Everybody see that? Did I need the distance formula? No, I didn't, because I was only measuring horizontal and vertical distances. Okay, with areas, think how many of those formulas that we just talked about involve bases and heights. As long as I line up the base horizontally, I'm not going to have to use the distance formula at all if I know coordinates, am I? Right? So to get the area of this thing, it's easy. The area is just 1/2 times, what's the height?
4.
4. Times the sum of the bases. What's the sum of the bases? 7 and 3, right? 10. So it's 1/2 times 4 times 10, which is what, 20? Okay, we got it. All right.